excited to introduce everyone to Holger. We were colleagues at the Swedish University of Agricultural Sciences in Uppsala a few years ago. And he is a mathematician representing the ecological domain science today, working on really important problems because he's trying to figure out how bringing mathematical tools and information theory tools to understand how long and how to better manage forests to capture carbon and combat climate change. Thanks, Holger.
So I don't know how really important it's so far because so far there are no applications. I'm mostly presenting a theoretical framework. But yeah, thanks for the nice introduction, Maria, and thanks for the entire committee for this nicely organized conference. And yeah, I'm happy to be here and to present some of my older ideas on information theory and compartmental systems, and some of very recent ideas from last week, I would say. So it might be a little bit confused at the end because it's still very confused in my head. So currently I'm a postdoc at the Department of Forest Ecology and Management at the Swedish University of Agricultural Sciences in Umeå. And I'm part of the Future Silviculture project, which intends to bring ecophysiological knowledge back into boreal forest modeling. And this domain is currently really dominated by purely empirical modeling, which I personally find pretty boring. And it also has problems for transitioning to a different regime in terms of climate change. During my PhD at the Theoretical Ecosystem Ecology group, led by Carlos Sierra in the Max Planck Institute for Biogeochemistry, I developed explicit formulas for the distributions of ages and transit times in carbon cycle models. And I did this by interpreting deterministic compartmental systems in a probabilistic way. And with the same approach, we afterwards introduced a novel entropy concept for this deterministic compartmental systems. And during this presentation, I'm going to introduce you to compartmental systems, this novel entropy approach, some very first rough ideas of applications. And in the second part, I will go completely wild and guide you through a widely speculative way of maybe reconciling the discrete Shannon entropy and continuous differential entropy. And then, since the two terms will be kind of pop up every now and then in the presentation, I just want to say some initial notes on them. So Shannon entropy is for discrete random variables, and it's a proper measure for information content. So if you get a value, it really means something. It is a proper information content. It's always non-negative, and it's also invariant on the change of units. Differential entropy for continuous variables, even though it looks very similar, has very different properties. Right? It can be negative. It's not a proper measure for information content, and its value alone doesn't make any sense. You always have to compare it relative to another differential entropy value if you want to learn anything from it. And the worst part of it, it's not invariant to change of units. And the reason for that is to make the formulas look very similar and to make any sense at all going from Shannon entropy to differential entropy via discretization, we have to throw away an infinite amount, which is represented by this red part. And this leads to all these problems here. So what are compartmental systems? Here I show you two examples. The first one is a three-pool compartmental system, the global carbon cycle model with three pools: terrestrial biosphere, atmosphere, and surface ocean. And outside of the system, we have deep ocean. And for example, we can also have fossil fuels entering directly to the atmosphere. The right system is a single three-carbon model with 10 pools. This is kind of the model I developed in the last 2.5 years, which was super frustrating. I'm never going to do something like this again. And yeah, but I come back to that later. I mean, that's just that you see what compartmental systems, box models, and so on look like. Why are we interested in compartmental systems? The first thing is they are very useful because they belong to a particular subclass of dynamical systems, the non-negative dynamical systems, right? And furthermore, they do not allow material to disappear or pop up spontaneously because they obey the law of mass conservation. And the very general nature of compartmental systems allows them to be used not only in biogeochemistry, as I'm usually doing, but also in biology, toxicology, ecology, hydrology, as you might know, and network theory, and many more disciplines. Usually, compartmental systems are described by a multidimensional system of ordinary differential equations. Here, x of t represents the vector of compartment contents at time t. Yeah, in my case, it's usually current, but it could be any kind of quantity that is conserved. The non-negative input vector function is called u here, and b is a function that maps onto compartmental matrices. What this is, I will explain in a second. Note that in general, both b and u can depend on the system state itself and on time. This means compartmental systems can be nonlinear and non-autonomous. In this presentation, because it's rather conceptual, we will focus on systems in equilibrium only. Note that such a system described this way is always well mixed. This means material entering a new pool is completely well mixed with all the other particles that are already in the pool. So particles within one pool are basically indistinguishable. Yeah, the matrix B is always supposed to be compartmental. This means that all diagonal entries are non-positive, all off-diagonal entries are non-negative, and all column sums are non-positive. The diagonal entries are the rates, the total output rates from a compartment. So minus BJJ is the output rate from compartment J, which includes output to other pools and output to outside of the system. Bij, the off-diagonal value, is the transfer rate from compartment J to compartment I, and the negative value of the column sum of column J, which we call Cj here, is the external outflow rate from compartment J, so to outside of the system. This ODE system, by these properties, is guaranteed to obey the law of conservation of mass, and consequently also the trajectory always remains non-negative. Now, after we had derived these explicit formulas for transit time and ages in such compartmental systems, my supervisor, Carlos, at some point came up with the question of complexity. And I was immediately intrigued, but why were we interested in complexity in the first place, right? First of all, it's an additional system property to age and transit time, which we can use to better understand the system and to compare different systems to each other. And further on, we can probably use something like that to compare model for model selection as well for parameter identification from maybe tracer experiments or something like that. Of course, there are well-established complexity measures for dynamical systems like topological or metric entropy. In our case, these linear, autonomous, and open compartmental systems, they are dissipative. This means that there are no positive Lyapunov exponents, and by Pessin's theorem, this means both metric and topological entropy vanish. So they are always zero, and we cannot use them for any kind of complexity measure, which means we need a different approach. So the first start was we were looking at this three-dimensional or three-pool system, and the second one is a two-pool system. And we were asking this very naive question, which model is more complex of the two? Of course, you would think the more compartments, the more complex is the model. You would think the more number of connections, the more complex is the model. The question is then how to give weights to the compartments and connections. What are the right weights? And I was then, my first approach was thinking, okay, let's imagine we are looking at one single particle at a random time, and we ask ourselves, where can we find it? In which compartment is it currently? So, and then you can think, how hard is it to answer this question? The next question is, okay, now we know maybe where it is, but where will it be next? So which will be its next compartment in its sequence of traveling through the system? And the next question then could be, okay, where has it been before? Which was the previous compartment? And so you can go on forever, basically. And this leads to the natural question, how hard is it to predict the particle's entire path through the system from the moment of its entry until the moment of its exit? And the idea is that we basically use a single particle approach. Instead of looking at the entire masses moving through the system deterministically, we zoom into the microscopic scale and are interested in the random path of a single particle traveling through the system. This path is a particular stochastic process called an absorbing continuous time Markov chain. And there's lots of theory on that out there, right? So then, for example, if you look at this from this system, then the question of distribution of the transit time you can find on Wikipedia. I'll ask you this question with the one particle, then we can ask, what is the probability distribution of such a path through the system? And once we know this probability distribution, we can just compute its entropy, and we can answer the question, how hard is it to predict the path of a particle through the system? Or equivalently, how much do we learn once we observe the path of a particle through the system? In general, we assume that our system is open, which means that every particle that enters the system will eventually, at some point in the future, with probability 1, also leave the system. And this is guaranteed by making the compartmental, by asking the compartmental matrix B to be invertible. And going from compartmental systems to continuous time Markov chains, we see that on the left-hand side, we have the properties of a compartmental matrix, and on the right-hand side, we have the properties of a transition rate matrix of a continuous time Markov chain. And the only difference is this inequality, which is here inequality. So this means on the left side, we lose some mass, and on the right side, it's a closed system. And in order to reconcile that, we just close our system by adding an environmental compartment to it. So every particle that leaves the system is now basically collected in the D plus first compartment, which is an environmental compartment. And then we're having a continuous time Markov chain on a D plus one-dimensional space. And the initial distribution we can simply compute by normalizing the external input vector U. What happens then is that our law of conservation of mass turns now in the law of conservation of probability mass. The path of such a thing, the particle travel through the system, is then described by a continuous time Markov chain X. And we say when X has the value K, this means that the particle is at that moment in compartment K. If X has the value D plus 1, then the particle has already left the system, it's already in the environmental pool. And once it is there, and it will go there by probability 1 at some point in time, once it is there, it will never leave this pool again. It's just stuck forever. So basically, when the Markov chain changes to D plus 1, this means that the particle has left the system. Now our question was, how hard is it to guess or predict such a path? So how does a path look like? In the end, a path is a finite sequence with a random length, we don't know, of pairs of random compartments C and times spent in this compartment T. So particle enters compartment 1 and stays there for time 1. Then it enters compartment 2 and stays there for time 2, and so on until it finally leaves the system. And if we sum over all these sojourn times in the different compartments, we end up also with the transit time through the entire system. Here I have a very simple example of how we could compute the path entropy of such a thing. Imagine we're having this three-pool system given by this compartmental matrix and this external input vector U. So the particle arrives at the system and has to start in one compartment, either compartment 1 or compartment 2. We can compute the probabilities beta from the input vector. And our first uncertainty is the first pool where the particle enters the system. And this is the Shannon entropy for a discrete random variable. So let's say the particle enters through pool 1. And then it will stay there for an exponentially distributed time. So we add another uncertainty here, which is the entropy of the exponential distribution. And this entropy now is a differential entropy. Right? So we already see that we are mixing discrete and differential entropies. Now the particle stays there for a while, and then we have the next thing. Particle jumps either to pool 2 or to pool 3. We add another Shannon entropy for the jump out of pool 1. Let's say it goes to pool 2, and then we have to add the uncertainty of how long it will stay in this pool, and so on and so on. Particle moves around until it finally leaves the system. Without showing you how it's computationally done, here we get the formula for the path entropy. The blue part is always the same here. It's always path entropy, just in kind of different notation. And basically the first part is the entropy of beta. So what is the first pool the particle enters the system from? And this is a Shannon entropy. And then we're getting while the particle is in pool J, it is subject to a superposition of D Poisson processes. D minus 1 Poisson processes govern whether the particle changes within the next millisecond, let's say, jumps to a different pool or it does not. And the last one is whether the particle jumps out of the system or it does not. Such a path entropy, of course, depends also on the length. How long is the path? How long does this particle stay in the system? And if we just normalize that by taking the average over the average uncertainty over the average path length, we end up with an entropy per unit time. And this here is just the same as this here up. And we can also, for example, compute the entropy, the average entropy per jump. So how the particle jumps so and so often between pools, and then it jumps out of the system. We divide by this number, and we get an entropy rate per jump. And this formula is probably closest to the example I showed before. So each time a particle visits a certain pool, it stays there for a differential. It stays there for an exponentially distributed time. So this is a differential entropy. And then after the next day, it has to jump somewhere, and this is then a Shannon entropy. The mathematical novelty here is that we introduced entropy rates here now for absorbing continuous time Markov chains, where in classical literature, entropy rates are always introduced for stationary processes. And here, this process is not stationary because at some point it just stops, basically. And even though it looks very heuristically to take the path entropy and then divide by the mean transit time or the mean number of jumps, it can be shown that those heuristic entropy rates are real proper entropy rates in the sense as Alex defined yesterday, for example, for stationary processes where the particle, as soon as it left the system, immediately jumps back into the system. And thus this over and over again. This gives you a stationary process, and those are the corresponding entropy rates of such a process. What I also don't show here is there is another way to compute the path entropy through the probability distribution on the path space. On the space of all possible paths, you can introduce a measure on that, and you can compute the probability density function, and you end up with the same path entropy in the end. And I don't show that here, but it's always nice to have the probability density of this thing, right? It's a kind of a powerful object to have. Here we see some first properties of the entropy rate per unit time. Each dot here is a compartmental system. Red dots have 4 pools, blue dots have 3 pools, for example. On the x-axis, you have the number of edges between the pools, and on the y-axis, we actually have an entropy rate. And we see that with increasing number of pools and increasing number of edges, there are systems that can have more and more entropy. But there might also be 4-pool systems, depending on their connections, that have a lower entropy rate than, for example, 3-pool systems with a different kind of connectivity. Coming back to our example from the beginning on this very naive question, here the 2 systems are highlighted. And if we think you can see here that the entropy rate, so the entropy rate per unit time for the 3-pool totally disconnected system is higher than for the 2-pool system with feedbacks. But we're having here these feedbacks. This means the particle can go on back and forth, back and forth, back and forth through the in the system until it finally leaves. This means that its mean transit time is much higher than in the totally disconnected system. This means that the paths are longer on average, which makes the path entropy higher. So we're already in a kind of a dilemma. Are we interested in the path entropy? Then this system has a high entropy. Are we interested in the entropy rate per unit time? Then this system has a kind of entropy. So we already see if we were to use entropy directly as a complexity measure, we would have to ask ourselves, what are we really interested in, and which kind of complexity? You're allowed to some kind of preliminary ecological applications, yeah?
When the chain restarts? Does it randomly start in one of these six? I don't understand how.
I mean, the absorbing mass exchange particle will never come back, right? But if we look at the stationary process I mentioned, where it already comes back in, then each time it comes back in, you have this input vector here, 1, 1, 1, which you normalize, but it is equally likely to start in each of the pools.
Okay, so that's how it is.
Yeah. Yeah. If here, for example, were a 0, then it would not start in the third pool, but in 1 or 2.
Right.
It depends on the input vector.
Right. But in that case, so I guess the reason I asked is in that case, I would use that a non-ergodic component, but if it's restarting and randomly choosing.
Exactly, that's the idea. So we are looking at a non-ergodic absorbing chain, but we can show that the quantities we introduced belong to an ergodic stationary chain, to a different one, right? And yeah, here we have a global carbon cycle model with 5 pools. They are non-woody tree parts, woody tree parts, plant vegetation, detritus, and active soil. And we are having this description here, just basically, but we introduce an environmental, how is it called? Environmental rate modifier. So let's say if psi is greater, then the system is faster. So we can psi basically link to some kind of global surface temperature. So with global surface temperature increasing, psi increases, the system becomes faster. Please note here that we don't look at any phase transitions or anything, or any transient dynamics. We only look at systems with higher or lower psi, so with higher or lower entropy speed, but always the system are considered in equilibrium, yeah, right? And we see that systems with higher surface temperature show a lower path entropy because the system becomes faster, path becomes shorter, path entropy goes down. But at the same time, we see that the kind of immediate uncertainty measured by the entropy rate becomes larger. So the immediate future of the system becomes harder to predict, which we can see here. So with higher surface temperature, we see the carbon stocks going down. This is because particles stay for a shorter time in the system. And for the same reason, the path entropy goes down. And in a reasonable range, the entropy rate per unit time, on the other hand, increases. So the long-term behavior is easier to predict, but the short-term behavior is kind of harder to predict. Another thing is, there is this famous paper by Friedlingstein in 2006 where they showed ensembles of models, modeling land carbon uptake or change in soil residence time and things like that. And if you have 1,000 models, then you have 2,000 predictions, right? And they are very diverse from each other. And this was 2006, and ever since then, this has not really changed. I mean, there are even more models, even more predictions. And I think, so for the soil systems, we have very diverse predictions and very diverse models. On the other hand, if we look in ecosystem models and we look at the photosynthesis part, it's basically always modeled by the same by the same type of approach, and it's always, and it has not changed much since the Facua photosynthetical model was introduced. And the reason of that might be the different system speeds. So photosynthesis and soil cycling happen on very different time scales, right? Photosynthesis on like milliseconds, seconds, minutes, and soil carbon turnover in decades, millennia, whatever you like. We see that here. Let's assume we can model the soil component cycling, carbon cycling, as a one-pool system, and we do the same for the photosynthesis. In a one-pool system, the entire path is perfectly determined by its transit time because the particle is either in the system or it has left. So there is no other thing. If you know the transit time, you know the path of the particle. This means that the path probability distribution is an exponential distribution, and here we see the entropy of the exponential distribution. If we look at the instantaneous uncertainty, then we have the entropy rate of a Poisson process here. So this shows the entropy rate. We see that the entropy, the photosynthetical system is much faster, and also then the entropy is much lower than for the slow soil system, which is much slower and much harder to predict. And there is the question, maybe because the system is so slow, models cannot do better than making bad predictions. And this is why we see all this spread out in the predictions for the future. Just maybe because the system is so slow. The same we see here for the entropy rate. And here we measure the system speed in inverses of years. This means that mean transit time is given in years. So now let's do something crazy. Instead of looking in years, we look at the same thing and compute the entropies in on the scale of milliseconds instead of years. So we see, of course, because it's a differential entropy, that the values change. And for the path entropy, at least the order is preserved, right? The slow system has still a higher entropy than the fast system. But this might not be the case for the entropy rate, for the instantaneous uncertainty. All of a sudden, just by changing the units, that we changed nothing physically, just changing the units we use for the computation, we see that the slow soil cycling system has now a lower entropy than the fast cycling photosynthesis. So differential entropies, entropy rates can lead to all kinds of comparison problems. Another example here I would have, this is the model I built basically. So this is a tree and this is a pine and this is a spruce. Carbon enters from photosynthesis into this transient pool E, from where it is distributed all over different tree organs. And then it moves around and does whatsoever. And here, the darker the color, the higher is the uncertainty of the carbon. So the higher is the uncertainty of what we know where the carbon atom will be next. Of course, the uncertainty is pretty high here in the transient pool because carbon has a lot of possibilities of where to go. And now we can ask ourselves, okay, we have a dark pool color. This means the instantaneous future of the carbon in this pool is very uncertain. Is this now a property of the underlying natural system, or is it just bad modeling, right? If it's an underlying property of the system, then we might have found some bottleneck in the modeling, so we cannot do better. But maybe we just build a bad model for it. Here we see the difference. So we check the entropies of pine minus the entropy of spruce. And we see that in most of the pools, the uncertainty is higher in the pines. So can we then say modeling pines is more difficult than modeling spruces? And one technical problem that arose here is the formulas I showed you for the entropy are all continuous in a sense, right? But the implementation of the underlying model is discrete. So we have to kind of reconcile already discrete and continuous entropy. Once we're having these entropy terms, we can think about maximum entropy. We've heard about it already a lot. And there are also problems because we can always increase the entropy of our system by adding more pools to it. So there is no upper limit. So looking for a maximum entropy model only makes sense once we already know the number of pools we are interested in. And the second problem is if we want to maximize the path entropy, we can always make the system slower and slower and slower and the paths longer and longer and longer and increase the path entropy as much as we want. So it's often better to maximize the entropy rate, but we have already seen what can happen to maximizing entropy rates or changing units. So it's a kind of a tricky business. One interesting measure you could have, let's assume you're having some given data and you're having a model, and your model is not the maximum entropy model. So you're having a positive distance from the maximum entropy to your entropy. This means that your model contains some additional information. And now you can look at this from 2 points of view. The positive one is, okay, the modeler knows something. He has some good intuition and put that into the model. So that's something nice. You can also think of it from a very bad perspective. The modeler put some information in the model which is not fundamentally based in the data, so the model is biased. So it's a matter of perspective, right? I have one simple example for a maximum entropy model. Assume we have given a certain number of compartments, we have given a mean transit time through the system, and we have given an input vector u. Then the maximum entropy model has this compartment matrix, which is basically just ones everywhere on the off diagonals. And on the diagonal, we have some value, some rate, which is chosen in the way that we keep the mean transit time constant. We see that this maximizing the entropy gives you the highest possible degree of symmetry, right? And so we see a very symmetric model here, and this also shows you that the entropy itself, or the entropy rate in this case, is not a good idea to choose as a complexity measure, because this thing doesn't look complex at all, right? And if you compress it, I don't know, in terms of minimum description, it will be pretty short. So it's not really complex. The entropy is very high, but it's kind of the white noise of the compartmental models, let's say. I will possibly skip this example. and come to some results on the path entropy and rates and entropy rates and so on. So we interpret the discrete compartmental system in a probabilistic way as a Markov chain. So we zoom in from the macroscopic scale to the microscopic scale. And then we can introduce entropy rates and path entropy and such things like that. We can use the maximum entropy principle for parameter identification or solving equifinality problems and things like that. It's also possible to extend this approach to non-autonomous systems by discretization over time. In that case, if we do that, we get to realize that the entropy rate per unit time at a fixed time t is really an instantaneous entropy of the infinitesimal future of the system. There are lots of already known limitations. We have seen that differential entropy is involved, so the value itself, if we compute it, doesn't make any sense unless we compare it to another differential entropy value that we computed in the same way, right? So we can only compare compartmental models to compartmental models. Even worse, we have a mix of Shannon and discrete differential entropy, which is already hard to interpret. We have kind of an alleviation for this problem because we can derive the path entropy as a proper differential entropy on the path space via the probability distribution that I showed you. I came to the conclusion also about the complexity thing, that entropy itself is of course not a good measure for complexity. And also that asking the question, as we posted at the beginning, is this model more complex or this model more complex? Without any context doesn't make much sense, right? You can always find complexity measures that order models differently. Without any context, the only thing that came to my mind recently would be an answer could be the minimum description length. So far, we walked up our path of knowledge and speculation on which is this. The path is the orange arrow on a very solid foundation, right? So everything is mathematically proven. It's everything fine. But now, what can we do with it? I would like to have a better integration of this model theory, entropy theory, with information content of measurement data. For that, we could use the probability density as a likelihood function in the AIC framework, because the AIC framework is also very closely related to maximum entropy. So I guess there is a nice connection. There still remains for me this question of minimal complexity given a data set and experimental setup. And without any context, as I mentioned, maybe the minimum description length is the complexity measure to go. We could also ask ourselves which would be useful contexts for other complexity measures. So this is already speculation. I think there could be something done, but we're not on a solid mathematical foundation anymore. And we can go further with some ecological philosophical ideas. Very often carbon uptake and partitioning between tree organs is modeled by optimizing a performance function. But I don't think that trees work with such a capitalistic approach, right? So optimal performance does not leave any space for redundancy, and without redundancy, you have no chance for survival on evolutionary timescale. So trees don't need to be optimal, they just need to be good enough. And on that topic, there is a very good book by Daniel Esmail that I'm just reading at the moment. So for long-term survival, there need to be resources to cope with extreme events or hard times, right? And these resources are basically built up by redundancy. So maybe instead of optimizing a performance measure, we should optimize some kind of redundancy under the side condition of short-term survival. And I think information theory needs somehow to be part of this optimization process. And another question that came to my mind recently is, life in the universe tends to decrease the entropy. So if life is there, we decrease the entropy in the universe. But how does this go together with the maximum entropy approach in ecological sciences? So that's kind of, I don't know. So now it's getting already unstable on our letter, but we can go even further. So there are some fundamental discrepancies. Uwe mentioned in your preparation course, which I found super interesting. You mentioned that the idea Gauss law can be derived from maximum entropy principle. I even heard that you can use the three fundamental forces, electromagnetic and strong and weak interaction, and maximum entropy to derive gravity. So which one is now the fourth fundamental force? Is it gravity or is it entropy? Maybe they are equivalent. In theoretical physics, they have this problem of the big versus the small, right? The relativity theory for the big topics and quantum theory for the quantum mechanics for the very small times for the very small scale, and the two seem to be irreconcilable. We have a similar problem in information theory with discrete versus continuous random variables, where we have Shannon entropy for discrete random variables and differential entropy for continuous random variables. And differential entropy is a relative quantity that makes only sense relative. So there is some connection to relativity theory. General entropy is per se discrete, like is quantum theory at the Planck scale, right? So there are connections between the two parallels. And then last week, I stumbled over a video on YouTube on serial numbers, which were introduced by John Conway. And the term serial numbers was later on coined by Donald Knuth. And serial numbers are an extension of the real numbers, even an extension of the higher per real numbers. And they contain infinitely big numbers and also infinitesimally small numbers. So we see here the real numbers, serial numbers, for example, contain all the natural numbers. And then omega is the first number that is bigger than every natural number, right? It's the first ordinal, so to say. And then we can continue with omega plus 1, 2, omega squared, and so on. Since the serial numbers can be shown to have the properties of an algebraic field, we can do algebra on them, and all the inverses except for the zero are also part of it. This means we have infinitely big numbers, and the inverses are then the epsilon are infinitely small numbers. We also have those. And then we come to classical measure theory, where 0 times infinity is defined to be 0 always. Very boring, no room for interpretation. But in the serial world, we can now zoom into this fixed 0 times infinity and see that there are different possibilities. We can compute epsilon times omega, which equals 1, and infinitesimal times an infinite number equals 1. Or we can compute epsilon squared times omega, which is epsilon. So we have a very, very infinitesimal number multiplied with an infinite number and still get an infinitesimal number. And my idea was, can we use this framework somehow to reconcile Shannon and differential entropy? And this is where we are really far off now. And our latitudes, and we are here. So they are lower than we have been at the starting point, because now we don't even know anymore what is a number. So we have introduced numbers from scratch if we want to work with serial numbers. But lucky enough, John Conway did that for us already. So serial numbers are already defined. What we have to do now is to understand this. To understand the algebra that exists, we have to introduce calculus, measure theory, probability theory, and then eventually we might be able to reconcile Shannon entropy with differential entropy under the common concept of some serial entropy, which then is hopefully a proper information measure, which means at least non-negative and independent on the unit change. So then, if all that works, then we are here, right? And once we are here, we have seen these parallels between Shannon entropy and differential entropy, and at the same time, quantum mechanics and general relativity. So if we are thinking really far out, then maybe we can use serial entropy to reconcile quantum theory and relativity theory. Right? It's hopefully as easy as that. So, during the last years, I was building this tree modeling model, which was super frustrating. And at that moment, when I clicked on submit, I fell from my chair and was lying there and was thinking about this. And I hope in Uppsala at the university, at some point in the 70s or 80s, they had this journal of wild speculations. I think this would perfectly fit there. So thanks a lot for your patience. And
yeah.
When you think about it, converging to what you expect to be the true entropy rate of the ergodic version of the chain.
The true entropy rate of the ergodic version of the chain is what I introduced here.
Right, but can you look at like shorter path lengths and calculate for some finite path length entropy divided by what your path length is, and then look at a convergence to some infinite path length? Does that make sense what I'm saying?
I think it's constant.
It's just constant for even a short, like even if you.
Because you by normalizing, by dividing through the mean path length.
Well, so I'm thinking about like if you look at the entropy over a block of only 5 symbols, 5 states, generally that's going to be higher than if you look at the entropy over your entire system. Like it must be at least equal or higher. So what I was thinking is this complexity idea. If there is a convergence like this, the area under the curve is often kind of tells you the cost to understand how actually unpredictable the chain is, which is one layer beyond just your unpredictability.
Yeah, this is something I would be super interested to talk about, because I have been struggling with this step, let's say, from the entropy to a reasonable complexity measure
Right.
a lot. And I had so many ideas, and I came only to the conclusion that it's really context dependent.
I agree.
Until maybe the minimum description length. But then I have the problem, how do we compute the minimum description length of this, for example, 2 or 3 point model I showed? But this is definitely something I've always been interested in. I have no answer, but I would be open for any kind of idea.
Chat about it.
Yeah.
I'm just trying to understand exactly how the math works. Like if there's something like this, like that would be a really interesting way to do it information theoretically. I also think, of course, the structure of your compartmental model, but I'm not 100% confident. How do you design these based on data or based on prior?
During my young ecological career so far, I was able to do 2 important things. I avoided working with data. And even though I'm a mathematician, I've never done any hypothesis test so far in my entire life, and I want to stick to that rule.
That's not a remark. So first to respond to this, maybe wake up. I personally it was don't use entropy here, use directly minimum description. This reminds me of it's like years ago, even more when I started. There was a PhD by somebody called Neyman, and he pointed out that predictive complexity were basically the setup that you talked about, from Jim Crutchfield, I think, where there's an infinite sequence, we look at entropy of past and future. In some situations, the complexity measures there actually coincide with what you get in the other, and some they don't. So I completely forgot about this. Dropped it down. And that was 20 years ago. So maybe it might be interesting to look at it again, maybe this afternoon, because I think there might be something to do here. So that was direct response to this, but then my other thing, not for this afternoon, but I actually disagree with your. I don't think they're so irreconcilable.
You mean the general relativity?
No.
And
what's really what you should probably do here is what often is done in information theories. You take a starting point, like a starting measure, which has to be a probability measure. So Shannon entropy, basically you can think of it as minus relative entropy compared to the counting measure on all natural numbers, but that's not a probability measure. Once you take as your background measure probability measure, so then the differential entropy becomes a KL divergence between so it's integral f log f divided by g, and g is a probability measure. And that actually has an interpretation in terms of bits, even though it's continuous. And also the Shannon entropy, it retains its information in terms of bits, and it becomes like, but it has an offset interpretation, like how many extra bits do you need?
Yeah, because through the
background measure, which has to be probability measure, so integrate to 1, then you can actually probably add the 2 and it's still meaningful. And well, not by me, but there are papers about this where there's a Topso, it's a famous information theorist from Denmark. He's written many papers where he shows that once you take this background measure, that basically all these problems with differential entropy, they kind of disappear if you look at relative distance to another measure. And then there are lots of things you can do. Of course, you add this prior measure there, which is something like a prior thing. But once you have that, I think many of your problems will probably disappear.
But you said it. You still have this measure relative to another thing, right? It's not in an absolute value meaningful. It's still relative.
So there, I am very skeptical about all this maximum entropy stuff, because I think also when you derive like all these laws of physics based on maximum entropy, is also start with it. Impose a constraint on the system, but there's this initial assumption that originally it was already kind of uniformly distributed in some sense. So you already had some kind of background measure. If your background measure was a very big system, my background measure was, it was really in this very, very specific state, and you cannot use these maximum entropy derivatives anymore, they fail. So I think we're kind of fooling ourselves into thinking that the discrete case has some kind of universal truth to it.
Mm-hmm.
But I think there we really secretly are also assuming when we use maximum entropy principles and so on. Like we started from a uniform measure in the beginning, and then we started imposing constraint into maximum entropy, and it's constraint, and we're really doing a minimum KL vector. It's another maximum entropy. That's my view on the world. So it's kind of, we're secretly doing this anyway.
What I find interesting there, if we look at, for example, the natural numbers, then we cannot have a uniform distribution on all the natural numbers, right? Because then each one would be 0, and then we sum them up, and they are still 0. But in the surreal numbers, we could have them. We could give each number the probability 1 over omega, and then we would have a uniform distribution. So I see that potential. I don't say there is the universal truth.
This is a great start. That's not. Do you have any last words you want to say?
No. I think I will. No, I think I will. I mean, I turned only 40, right?
All right. We're going to take a break. Let's